Welcome back to Physics 191. I'm Gerard Blanchard. Last time we talked about momentum situations, which were usually collisions or sometimes explosions, and we introduced the idea of coefficient of restitution, which measures the elasticity of a collision. Elasticity being measured by our letter E, which goes from 0 for what we called a perfectly inelastic collision to 1 for a perfectly elastic collision, and the coefficient of restitution E was equal to minus the speed with which the objects departed from each other after the collision divided by the speed with which they approached each other before the collision. And so that gives us a little bit more information to use in collisions, and so we can solve a greater range of questions. We'll call our new type of situation that we can deal with still a momentum situation, but we'll add that it is also an elastic collision. So how do we identify this? Well, we have two objects interact, which changes their speed, and we know the coefficient of restitution. Our general equation is still that the total momentum in the x direction initially is equal to the total momentum in the x direction finally, but we also have the additional information on the coefficient of restitution, which is equal to, in an equation form, minus v2x final minus v1x final divided by v2x initial minus v1x initial. Now we'll only use this for one-dimensional collisions. Two-dimensional collisions using the coefficient of restitution are beyond the scope of Physics 191. So let me give you a question that you can answer. A bumper car with one rider in it, which has a total mass of 200 kilograms, moving at 5 meters per second, collides with another bumper car with two riders in it, which gives it a mass of 250 kilograms, that is initially at rest. The coefficient of restitution between the bumper cars is 0.75. What is the velocity of each car after the collision? So we have an elastic collision. It's not perfectly elastic. It's not perfectly inelastic, but it has a coefficient of restitution of 0.75, which gives you another equation to use. So go ahead and set this situation up and list all your knowns and unknowns and list your equations that you'll use to answer this question. Go ahead and get a head start and see if you can stay ahead of me on this one. Okay, here's our situation. This will be our x-axis. Here's car 1, 200 kilograms, and it's moving at 5 meters per second. It collides with the other car, which is moving at 0 meters per second. This is initial. Our initial situation. And our final situation is that they have bumped each other, and we'll call the speed of this one v1x final, and the 250 kilogram car, we'll say it's moving with v2x final. It's our final situation. And we know that the total momentum initially is equal to the total momentum finally. So P total x initial equals P total x final. And we also know that the coefficient of restitution, E, is equal to 0.75. So this gives us our two equations. We're going to have two unknowns, V1x final and V2x final, so we need two equations in two unknowns. P total x initial, we have 200 kilograms moving at 5 meters per second, so that would be 200 times 5 plus 250 times 0 plus 0 equals 200 V1x final plus 250 V2x final. And so we have 1,000 over here is equal to 200 V1x final plus 250 V2x final. Let's use our, which gives us two equations, one equation and two unknowns. We need another equation. Let's use our elasticity equation. So that would be 0.75 is equal to negative V2x final minus V1x final over V2x initial minus V1x initial, or 0.75 is equal to minus V2x final minus V1x final divided by V2x initial, which is 0, minus V1x initial, which is 5. So here I have a negative divided by a negative. I'm just going to make those positive. And I'll multiply both sides by 5 to get this 5 out of the denominator. Or I have 0.75 times 5 is equal to V2x final minus V1x final. And as we've done before, I will add V1x final to both sides. And let's see, 0.75 times 5. 0.75 times 5 gives me 3.75. 3.75 plus V1x final is equal to V2x final. And once again, all of this right here is equal to V2x final. So what I will do is I will take this and substitute it in for V2x final. And what does that give us? That gives us 1,000 is equal to 200 V1x final plus 250 times 3.75 plus V1x final. Or, let's see, that gives us 1,000 is equal to, we have 200 V1x final, and we have 250 V1x final. So that's going to give us 450 V1x final plus 250 times 3.75. So 250 times 3.75 is equal to 937.5, which I will subtract from both sides. I'll have 1,000 minus 937.5 is equal to 450 Vx final. So I will also divide both sides by 450. And that gives me 1,000 minus 937.5 divided by 450 is 0.139 equals Vx final. And that would be 0.139 meters per second. So, car 1 is moving at 0.139 meters per second after the collision. So that car went from 5 meters per second down to 0.139 meters per second. We can now figure out the V2x final, now that we know V1x final. And V2x final is 3.75 plus 0.139. Which is going to be 0.139 plus 3.75 is going to be 3.89. 3.89 meters per second is V2x final. So this car is now moving at 3.89 meters per second. So we have answered the question that we were asked. Now I'm going to use this example and I'm going to teach you something that we don't normally teach in Physics 191, but it's something that follows naturally from this course and something that is within the range of what can be understood from Physics 191. And that is, we're going to use momentum ideas and we're going to estimate the forces involved in a collision. And to do that, we're going to consider the exchange of momentum between car 1 and car 2. And what we see is we have car 1 moving at 5 meters per second, and it collides with car 2 at 0 meters per second, and car 1 exerts a force on car 2 and gives car 2 momentum. So we can write that the change in momentum of object 2 is equal to the force that object 1 exerted on it, the force that object 1 exerted on object 2, or car 1 exerted on car 2, times the change in time. This is the equation that we derived early on when we were talking about the change in an object's momentum. The change in momentum is the force applied to an object times the change in time. Now, if we were to consider both objects, then the total change in momentum would be 0. But when we just consider the transfer of momentum from object 1 to object 2, then this is not 0. What is the change in object 2's momentum? That would be P2x final minus P2x initial is equal to the force that object 1 exerted on object 2 times the change in time. The final momentum of car 2 was 250 kilograms times 3.89 meters per second minus its initial momentum, which is 0, says the force of object 1 on object 2 times the change in time. So if we know the change in time, then we can calculate the force that car 1 exerted on car 2. Well, we don't know it exactly, but we can estimate it. We know that car 1 was moving at 5 meters per second, and we know that during the collision, it could only have moved about the distance of its bumper. So we know the velocity of car 1 before. We know that at most it moved the width of its bumper, so we can estimate the time using V1 x initial plus V1 x final over 2 is equal to delta x over delta t. And we know both the initial velocity of car 1 and the final velocity of car 1. And that was 5 meters per second plus 1.39 meters per second over 2 is equal to the distance that car 1 moved during the collision. And we'll estimate that to be the width of the bumper, which is a few centimeters. So I'll say 5 centimeters, 0.05 meters divided by delta t. And all of this works out to be, let's see, 5. I'm sorry, this was 0.139. 0.139. 5 plus 0.139. 5 plus 0.139 divided by 2. This is 2.57. 2.57 is 0.05 meters over delta t, which if we multiply both sides by delta t and divide both sides by 2.57, we have delta t for the collision of 0.05 divided by 2.57. And we have 0.05 divided by 2.57. And we have 0.02, I'll round off, 0.02 seconds. So in this way we've estimated, this is just an estimate, we've estimated that the collision between the bumper cars took place in 0.02 of a second. It seems reasonable. It's a quick jolt between the cars. So now with this estimate of delta t, we can take 250 times 3.98 and divide both sides by delta t, 0.02 seconds. And that will be the force that car 1 exerted on car 2. And that would be 250 times 3.98 divided by 0.02, and we can calculate that the force that car 1 exerted on car 2 for that very short period of time was about 50,000 newtons. This is just an example, just an estimate. I'm sorry, this is just an estimate, but it's probably pretty close. So you can see that when objects collide, that there are enormous forces involved for a very short time. So that's the end of Chapter 7 and momentum and collisions. And our next chapter, Chapter 8, is torque and angular momentum. So we'll be talking more about rotation and also rotational equilibrium, which is a very useful topic. First, let's introduce the concept of torque. Before we do that, however, let's think about Newton's second law. We know that unbalanced forces cause acceleration, or, as Newton's second law says, the acceleration of an object is the total force on that object divided by its mass. We also learned about rotational acceleration. So what causes rotational acceleration? And the answer is torque. Torque, which we'll symbolize with a lowercase Greek tau, appears in an equation similar to Newton's second law, which would be angular acceleration, alpha, is equal to the total torque on an object divided by something that we call rotational inertia, and which we symbolize with a capital I. So our analogous equation to Newton's second law for rotation is angular acceleration is equal to the total torque on an object divided by rotational inertia. We'll talk about rotational inertia in a bit. Let's talk about torque first. The torque on an object depends on three things. It depends on the force that is applied to an object. It depends on the distance that force is applied from the pivot point, and it also depends on the angle of the force. Let me demonstrate that for you. Here I have a wheel, and if I want to make that wheel rotate, well, at first I have to apply a force to it. If I have zero force, then I have zero angular acceleration. So that's the first thing. The torque depends on the force that I apply. And also, the more force that I apply, the greater the angular acceleration. So, if I apply a small force, I can get a small angular acceleration. If I apply more force, I can get a greater angular acceleration of this wheel. The other thing that torque depends on is where I apply the force. If I apply the force directly at the pivot point, well, that wheel's not going to rotate. If I try to push on the pivot point, obviously the wheel's not going to rotate. So if the distance of my force from the pivot point is zero, then obviously I'm not going to get any torque. If I apply a torque very close to the pivot point, I get less torque, less angular acceleration. But if I apply a force far from the pivot point, I can get a greater angular acceleration. So the distance that I apply my force from the pivot point increases the torque that I apply to the wheel. And finally, the direction of the force matters. If I were to push directly inward towards the pivot point, then I would not give this wheel an angular acceleration. If I were to pull directly away from the pivot point, I would also not give this wheel an angular acceleration. The best that I can do is to push in the direction perpendicular to the line towards the pivot point. So if I push perpendicular, I get a greater angular acceleration than if I pull directly away from the pivot point or push in towards the pivot point. So torque depends on three things: the amount of force that we apply, where I apply the force. Remember, applying it in the middle doesn't do any good, and applying it close to the center, it's hard to get that wheel to spin too. But if I apply the force further out, I can get a greater torque, which will give the wheel a greater angular acceleration, and also the direction. Pushing directly towards the pivot point or pulling directly away from the pivot point doesn't give me a torque. My best thing that I can do is to, if I'm going to apply a torque at this point, then I want to apply it perpendicular to the line to the pivot. So that would be up in this case. However, if I were to apply my force right here, then I would have to be perpendicular to the line from here to the pivot, meaning straight up now is zero torque. So I have to apply some force perpendicular to the line towards the pivot. So in this direction, for example. So torque depends on three things: force, where you apply the force, and the direction in which you apply the force. Now we'll give you an equation to calculate torque. We will symbolize force with an F, the distance that you apply the force from the pivot point by R, and we'll make theta be the angle between the force vector and the line from the point where you apply the force to the pivot point, or the axis. And torque is then equal to the radius times the force times the sine of the angle between the force and the direction to the pivot point. Now, why is it sine? Well, if I push directly towards the pivot point, then the sine of theta would be, well, then theta would be 0. Or if I pull away from the pivot point, then theta would be 180, and the sine of 0 and the sine of 180 are both 0. Our biggest torque occurs when we have a 90-degree angle between the force and the direction to the pivot point, and that's where sine of theta is biggest. So torque is equal to force times the distance at which you apply the force times the sine of the angle between the force and the direction to the pivot point. So we can write torque in three different equivalent ways. One is that torque is equal to the force times the radius times the sine of theta, or the torque is equal to the perpendicular force times the radius, or the torque is equal to the force times the perpendicular radius. And as I said, these are all equivalent ways of writing torque. They're all mathematically equivalent. These equations give us the magnitude of the torque, but we have to talk about the direction of torque. A counterclockwise torque is considered positive, and a clockwise torque is considered negative. This is similar to the direction of an angle that you learned in trigonometry. In trigonometry, you learned that angles increase in the counterclockwise direction. And so a counterclockwise torque is considered positive. A clockwise torque is considered negative. And finally, let's consider the units of torque. Well, it's just torque is a force times a distance, so torque would be in units of newtons times meters. You may have, that's our basic metric units of torque. It could also be any units of force times any units of distance. So you may be more familiar with torque in terms of foot-pounds. That's the unit of distance times the unit of force. So foot-pounds is a very fine unit of torque, but it's not our basic metric unit of torque, which will be Newton meters. Okay. This brings us back to equilibrium, because when an object is in equilibrium, it is at rest and it remains at rest, or it's moving at a constant speed in a straight line. and it is not rotating and it stays not rotating. Or it could also be a case where it rotates at constant angular speed. Therefore, for an object in equilibrium, the total force on the object is zero, but also the total torque on an object is zero. So, as I said, whenever we think about an object being in equilibrium, we think of something that is not moving and stays not moving, but also its angular acceleration is zero, which means that the total torque on that object must also be zero. So this brings us back to our equilibrium situation. And now we think of an equilibrium situation as being an object that's at rest and it remains at rest, or it's moving at a constant speed in a straight line, and the object is not rotating and it stays not rotating, or it's rotating at a constant angular speed. And now we have three general equations to deal with equilibrium. That would be the total force vector on the object is zero, which is the total force in the x direction is zero, and the total force on the y direction is zero, and the total torque on the object is zero. Now we have to make some notes about this. One is, now when we're calculating torque, we have to consider where are the forces applied. How about weight? Where is weight applied to our body? Well, weight acts as if all of the force is applied at the center of gravity of an object. So for uniform symmetric objects, this would be the geometric center of the object. And finally, if an object is not rotating, then we can consider any point to be the axis around which it's not rotating for the purpose of calculating torque. So, now in equilibrium, we have three equations. Let's take a look at an example where you would apply this. In the diagram, you can see a house painter who's standing on a uniform horizontal platform that's held in equilibrium by two cables attached to supports on the roof. The painter has a mass of 75 kilograms, and the mass of the platform is 2 kilograms. The distance from the left end of the platform to where the painter is standing is 2 meters, and the total length of the platform is 5 meters. And we have two questions. How large is the force that the left-hand cable exerts on the platform? And how large is the force that the right-hand cable exerts on the platform? Or in other words, what is the tension in the two cables? What I would like you to do is I would like you to draw your diagram of this situation, list your knowns and unknowns, and think about the equations that would apply to this. I'll give you a few seconds to get started on that. Let's go ahead and get started and think about how you would use your equations to answer this question. Okay, the central object in this situation is the board, or the platform. That is what all of the forces are being applied to. And what are the forces? We have force left from the tension in the left cable, force right from the tension in the right cable. Let me draw in my axes. I'm going to call this X. I'm going to call this Y. We have the painter standing on the platform. He is standing 2 meters from the left end. So if I call this 0 and this 2 meters, then the painter is standing on the platform and he is exerting a force on the platform equal to his weight. And his weight is mass times G, 75 times 9.80. So he is exerting a force on the board of 75 times 9.8 of 735 newtons. The cable over here is 5 meters from the other end because the total length of the board is 5 meters. And we have to include the weight of the board. Well, since the board is uniform, we will apply the weight at the center of gravity of the board, which is also the center of the board. So right here at 2.5 meters, we will have the weight of the board, which is equal to its mass times G, which is equal to 20 kilograms times 9.80. So we have a force of 20 times 9.80 of 196 newtons on the board at its center. So let's just review this. Here's the board, which is what everything is exerting a force on. The 4 forces are the tension from the left-hand cable applied at the left end of the board, which we'll call X is equal to 0. We have the weight of the man pushing down on the board at X is equal to 2 meters, and he's pushing down with a force equal to his weight, which is 735 newtons. We have gravity pulling down on the board, and we're going to put the gravitational force at the center of gravity of the board, which is the center of the board. And so at 2.5 meters, we add a force equal to 20 times 9.80, 196 newtons. And then finally, we have the force on the right end of the board from the right-hand cable, and that is 5 meters from the left end of the board. So at this point, we have diagrammed the situation. We've listed all of our knowns and unknowns, and we are ready to identify this as an equilibrium situation. Which means that we now have 3 equations. Force total X is equal to 0. Force total Y is equal to 0. And our new equation of torque total is equal to 0. Force total X, we have no forces in the X direction. So 0 equals 0. Which is true, not helpful, but it's true. Not helpful in this case, but it's true. Force total Y is equal to 0. Now it gets interesting. We have force left and force right pulling upwards. So that would be force left plus force right minus 735 newtons and 196 newtons downwards minus 735 minus 196, and all of that equals 0, which tells us force left plus force right equals, I'll add these two together and then add them to both sides. So force left plus force right equals 735 plus 196 equals 931 newtons. That's useful. That tells us what force left and force right have to be added together, but it doesn't tell us what they are individually. In order to get that, we'll have to go to our new equation, our torque equation. To use our torque equation, however, we have to choose a pivot point, which can be any point. To be most useful, we should put the pivot point at the location of an unknown force. And the reason why that is that will eliminate one of our forces. One of our torques, I should say. Okay, so I am going to choose to put the pivot point here at the right end, at the left end of the board. Make that my pivot. And I will measure all of my torques from that pivot point. So now we have to add up all of our torques. Remember that a counterclockwise torque is a positive torque. The only force here that will turn the board in the counterclockwise direction, if this is our pivot, is force right. Okay? This is our pivot point right here. So I'll hold the board steady right here. Force right will pull the board in the counterclockwise direction, giving us a counterclockwise torque. This force will pull the board in the clockwise direction, giving us a clockwise or negative torque. This force will push the board in the clockwise direction, giving us a negative torque as well. So force right is the only force with a positive torque. Okay, so our torque is force right times the distance that force right is from the pivot. So force right times 5 times the sine of the angle between force right and the board, which is a 90-degree angle, sine of 90 degrees. Then we have to subtract off the torque from gravity on the board, which is going to be minus 196 newtons times a distance of 2.5 meters times 2.5 times the sine of the angle between this force and the board. And you can see that this force and the board also make a 90-degree angle, times sine of 90 degrees. And then I'll also have to subtract off, the torque from this force, which is 735 newtons times 2 meters from the pivot, times the sine of the angle that this force makes with the board, which is also 90 degrees, and all of that equals 0. Okay, so we have a counterclockwise or positive torque from this force, a negative or clockwise torque from these two forces, and this force over here is applied exactly at the pivot, so it's neither clockwise nor counterclockwise, which gives it 0 torque. Okay, all of these sine of 90 degrees is 1, so all of this simplifies to force right times 5 minus 196 times 2.5 minus 735 times 2 is equal to 0, or force right times 5 is equal to, and I'll multiply this out, add them together, and then add them to both sides. So let's see, we have 196 times 2.5 plus 2 times 735 equals 1,960, and then dividing by 5 gives us force right is 1960 divided by 5, or force right is equal to 1960 divided by 5 is 392 newtons. And now that we know force right, we can come to this equation right here and say force left plus force right is equal to 931 newtons, or force left plus 392 is equal to 931, or force left is equal to 931 minus 392, or force left is equal to 539 newtons. So using our Newton's first law equations and our new torque total equals 0 equation, we're able to separately calculate force left and force right, which we would not have been able to do using just our x and y equations. So, the important things here are that we identify the central object of a situation, or the object upon which all the forces are being applied, and we pick a convenient point to call the pivot point, which is usually a point where we have an unknown force acting so that we can eliminate one of the torques. And then we apply our equations. The total force on an object is 0, which the total force in the x direction, and the total force in the y direction. Sometimes, as in this example, we don't have any forces in the x direction, but that's okay. It's still, the total forces are still 0. So the total forces in the x and y direction on the object are 0. And now we know that if an object is not rotating, then the total torque on the object is 0, which gives us another equation so that we can deal with more unknowns. And so that is our equilibrium revisited. If we were engineers, we would call this statics. This is what an engineer would call a static situation. And we'll be doing more of this. This is a very important topic, so we'll do many more exercises applying this. Until then, think physics.